Hi everybody, this is going to be our note for 2.5, Derivatives of Quotients. So, all of Chapter 2, we have learned about many different rules for finding the derivative. So below, in the little box I have below this paper, is a list of all the rules we've learned so far. But just out of curiosity, if I didn't have the little box here, would you be able to recite these rules? Maybe to a friend, classmate, to maybe grade 11 who's thinking about taking advanced functions and or calculus. Would you be able to write out the rules if I asked you to? Or can you maybe just use the rules if I give you a question? So I'm not going to ask you necessarily to write out the actual rules, but just something to think about. How well do you know these rules? So we have the product rule, the chain rule, power rule, and all of these other ones we got learned in 2.1. So the last rule we're learning about involves quotients. So there are two methods you can use to find the derivatives of quotients. One way we already know about, we just have to change our equation a little bit, but I just want to forewarn you, there is a lot of different calculations we're going to be doing. It's interesting though, because we're going to be doing stuff that you learned in grade 9, grade 10, grade 11, even all the way up to like yesterday's lesson. So it really is testing all of your math skills that you've learned all throughout high school. So let's take a look. So if I'm differentiating a simple quotient function, where I have it like if a function q at x is equal to f at x over g at x, where these are differentiable functions, and g prime at x does not equal 0, what I can do is I can just express this quotient as a set of two factors. And we're just going to move the denominator to the numerator here and just change the exponent to -1. So if I set it like this, then I can just find the derivative like this, which looks very confusing. But all this really is if I'm having these here, I'm just using the product rule, and then I'm going to be using the power rule here as well. So we actually see that here. This is just this part pretty much is like the power rule. So if you're like, oh, I don't understand how we're doing this, what does all this stuff mean? Well, again, this is just saying what our power rule was from yesterday. So once we get to an example, I think this will make a bit more sense, just like usual. So our example one says differentiate, I forgot the letter here, we're just going to put q. So differentiate q at x being this, and then state the domain of q at x and q prime at x. So I'm going to start just by writing out my equation again. We can put any letter here, but because our definition is q, I just chose q here. So I'm going to have this is 5 over x to the power of 3 plus 4. So if it's a simple quotient function, something like this, we have the option of, remember this is on the, in the denominator, this is to the exponent 1. So if I were to move this to the top, I would get that exponent becoming a negative. So we get -1 there. And that just kind of goes along with our negative exponent rule. Like if I had x to the power of -2, that's the same as saying 1 over x squared. Like that negative goes to the bottom and it becomes positive. Well, I can do the opposite. I could move this to the top and then make it a negative like we did here. So once we get up to this point, I really have two factors. So what we're going to do is incorporate our product rule here. And we can refer to our top here if we want, like the product rule. This is the one where we set the derivative of the first times the second plus the derivative of the second times the first. That's our product rule. So I think it was a bit clear before when I kind of set up our equations on the side and then kind of substitute them back in. So let's say that this one is going to be our f at x. And let's say this is going to be our g at x. So now we're going to find, when we're doing our derivative, we should find the derivative of both of these because we'll have to, according to our product and power rule, we have to find the derivative. So derivative of this one is going to be 6. And when we get to the derivative of g at x here, we have to incorporate what we learned before about our power rule, which is again just a type of a specific example of the chain rule. So here I'm going to take the derivative of the outer function. So I'm going to move the exponent here. and then keep the inside the same. Still subtract the exponent from 1 here, it becomes negative 2, and then multiply that by the derivative of the inside of the brackets, which in this case would be just 3x squared. So I have my f at x and g at x, my f prime at x, and my g prime at x. So we just have to remember that here we had to do the chain or power rule. Again, the power is just a type of specific example of the chain rule, so power rule. So now I'm just going to do my product rule here, incorporating all of these. So we can say if you want, we can write out our power rule here, or sorry, our product rule here. Go to the first times the second plus the derivative of the second times the first. So we have f prime at x we said is 6, and then we have g at x being this, plus g prime at x, which we said is this whole thing, and then this is the g prime at x, so this has to also be multiplied by f at x, which is this. So before I do my next step, I'm just going to kind of simplify this a little bit. I'm just going to do the negative 1 times 3x squared, which would give my next line to be this. Okay, so now what I'm going to do actually is I'm going to do a common factor. And I'm going to common factor by, well, for each of these terms. And I'm going to do it by the kind of the binomial that they have in common. So the binomial that they have in common is the x to the power of 3 plus 4. It's the same for both of these. So what we're going to do when we common factor and we have a negative exponent, the common factor is always the lower number out of the negative exponents. So in this case, I'm going to be common factoring out from this one. Well, for both of them, really the same one. And since negative 2 is a lower exponent, I'm going to divide both of these by x to the power of 3 plus 4 to the power of negative 2. So whenever I do a common factor, I always bring my common factor to the front. Sorry, I'm just going to write this here. Common factor. So when I do this, I bring my common factor to the front, and then I'm dividing both of these terms by this common factor. So if I do that, I can use square brackets here. Well, the 6 is pretty much just going to stay there. And using my exponent laws, which goes back to grade 9, I have negative 1 subtract negative 2. So it's not negative 1 minus 2, negative 1 subtract negative 2. And if I did that, I should get x to the power of 3 plus 4 to the power of 1. And I'm going to do this over this common factor for this one. These will cancel out. So I'm just left with negative 3x squared, 6x minus 5. Now you might be wondering, how can we simplify this further? Well, I can kind of simplify this. I know it's kind of a small one to fix, but we can do that. 6x to the power of 3 plus 4 minus, not plus, should be minus 3x squared times 6x minus 5. Well, I can see between these two coefficients that I can probably common factor out another number here. I can common factor out a 3. So if I common factor out a 3 here, I'm going to start writing it over here. The 3 is a common factor, so I bring it to the front. Always bring your common factor to the front. And then inside the brackets we have left over 2 x to the power of 3 plus 4 minus x squared times 6x minus 5. So now if we want, we can just start expanding things. So I'm going to write this as 3 x to the power of 3 plus 4 to the power of negative 2. We're going to get 2x to the power of 3 plus 8 using our distributive property here, minus 6x to the power of 3 plus 5x squared. Oops, I just realized I'm not showing that there. So again, a lot of simplifying here, a lot of just very small calculations. So I do have my negative exponent here, so I'm going to move that now back to the denominator. So I'm just left with this now on the numerator. So I have this over x to the power of 3 plus 4 to the power of 2. So then I can simplify this further. I could do my expanding here, collecting like terms, distributive property again. I'm just going to leave it here. I mean, if we were doing calculations and I wanted to simplify it further, I could and then just input my values. But if I wanted to stop here, I could also do that. It just means more calculations as we kind of move into the question. But at this point, we just want to kind of state the domain and range. So we could just collect like terms, distributive property, and get the numerator simplified. But since we're just working with domain, we only really care about the denominator here. So in our domain, it looks like we have it so that the denominator cannot be equal to 0. So this cannot equal 0. So if I isolate for x now, I get negative 4. And then I get x cannot be equal to the cube root of this. So this is pretty much my domain here, where x is also any real number. So that is one way we can do the finding the derivative of a quotient, of a fraction. So put it into, moving the denominator to the top and changing the sign of the exponent, and then just doing product rule until we get to this point. So let's do another example. So yeah, that was a lot of calculations. There's a lot of work we had to do. The toughest part, I would say, is doing the factoring with the kind of negative exponent. Maybe we don't have a lot of practice with that, but we're going to see that happening in this example as well. So we're going to try it again. So let's start with, we're differentiating this. Sorry, I forgot I think it just cut off when I put it as a Google Doc, so that's maybe why it's like that. So we're going to have, I'm just going to rewrite this again. Q at x is equal to x plus 3, and then square root of x squared minus 1. So I'm just going to change the square root into an exponent. I'm going to do it later anyway, so I might as well just do it now. So we get that. Sorry, this is a 2. So then before we said, well, if I have this in the denominator, let's move it to the numerator and then just change it to a negative exponent. Like that. So now when we see it like this, I have these factors here that are binomial, so we have to do our product rule here. So derivative of the first times the second times the derivative of the second times the first. So let's actually again write those out again. I'm going to write out f at x is equal to x plus 3, and g at x is equal to x squared minus 1 to the power of negative half. And I can see that maybe this is hard to read, so I'm going to zoom in a little bit. I'm writing a little bit smaller because we're going to be using all of the space for this work. So I'm going to find the derivative of both of these. f prime at x is just going to be 1, because this is going to be 0. Derivative of just x is going to be 1. Derivative of this, well, we have to incorporate our power rule again. So I'm going to move my exponent to the front. Subtract it by 1. I get negative 3 over 2. And then I multiply this by the derivative of the inside, which we just get 2x. So remember, we treat this as the outside function, so we do this to the front, subtract it by 1, and then we keep the inside the same, but then I multiply this by the derivative of the inside of the brackets. So we get this. So now I have this, 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 and this. We can now do our product rule to answer this. So we have q prime at x. Actually, I'm going to give myself a little bit more space. Q prime at x is equal to derivative of the first times the second plus the derivative of the second times the first. So let's just substitute what we have. We said f prime at x is 1 here. We're going to get 1 times g at x, which we said is x squared minus 1 to the power of negative half, plus g prime at x, which we said is this whole thing. We have negative half times x squared minus 1 times the 3 to the power of, to the power of negative 3 over 2 times 2x, and then multiply that by f at x, which we said is x plus 3 here. So I'll move it over now. I just wanted to let you know how we got what these are. Got these from here. Just put them in here right now. My next step is just to kind of clean up what's going on here. So just collecting up, we don't need to have the 1 there. I'll just get rid of that. And then we have negative 1 over 2 times 2x. Well, I could just multiply these. We're going to get negative 1x, or negative x, x plus 3, and then x squared minus 1 to the power of negative 3 over 2. So just cleaned up some of the, just like pretty much these two. So now we get to this point again. I'm going to divide by a common factor, and because we see that these have the same x squared minus 1 inside the brackets, this is going to be our common factor. But we're going to choose the exponent that is the lower exponent out of the two. So between negative 1 over 2 and negative 3 over 2, negative 3 over 2 is the lower number, so that's going to be my exponent for this common factor. So like always, bring the common factor to the front, x squared minus 1, negative 3 over 2. Well, this divided by this, if I get negative 1 over 2, and I subtract it, negative 3 over 2, I'm just going to double check, I end up getting just 1. So I'm going to get, well, like that. And then I'm going to add to that, well, these cancel out. So I'm left with just negative x, x plus 3. Sorry, you might be wondering where this 1 came from. This was the one from up here, but I forgot that I got rid of it already, so I'm just going to erase it right now. So that's where the... Anyways, if the 1 was there, 1 times this is just this anyway. So now we have this. So now if I wanted to, we could kind of collect our like terms here. We could also put this on the bottom of our fraction. So I could get x squared minus 1 minus x times x plus 3 all over x squared minus 1 3 over 2, and that negative 3 over 2 becomes a positive 3 over 2 here. We'll then simplify the next, simplify the numerator. Minus 1. I have to do distributive property here, so I have to get negative x squared minus 3x over this. So then I could keep simplifying this, but I'm kind of out of space right now. I could also change this to be instead, if we know how our rational exponents look like, I could just write this as well. Because this means the same thing. Denominator being the square root, and the numerator is what this is to a power 2. So again, I just care about the denominator since we're talking about domain. So my domain works out that x squared minus 1 has to be greater than 0 because we have a square root here. So we know it cannot be equal to 0, but it also can't be a negative number. So this has to be greater than 0, which if I isolate for this, get x squared as greater than 1. So my graph has to be less than negative 1, but x also has to be greater than 1. And that'll be my domain. So again, a lot of work being done here to do this. So what do you think? Something that's having to factor out that negative rational exponent is kind of annoying. So we can also use the quotient rule, or a quotient rule like this, but we also could summarize it like this, which is a bit more user-friendly, where we have q at x is equal to f at x at g at x, or when this happens. If they're both differentiable, functions, and the denominator is not equal to 0, we could write it like this instead. And this kind of looks like our product rule, but instead it has subtraction. So just to show that, I'm going to write my product rule here. And they look very similar, except instead of addition, we have a subtraction here. And the denominator now is just g at x squared whenever I want to do that. So let's now try this example, but we're going to use this equation to help us this time. So I'm going to rewrite my equation again. Again, this got cut off. So q at x, I forgot the wrong part this time, is equal to this. I'm going to rewrite it. And let's just on the side here again write out what f at x is. That's our numerator. And then we'll put our denominator here as well. Because I still need f at x, f prime at x, g at x, and g prime at x. So we might as well just list these here. And then find the derivative. So just using those rules we learned in 2.1. And we get these. So now I'm going to put these into this equation, and I'm going to rewrite this equation again. Do you have to? No, you could just put them in, but I'm just going to do it because it's our note, and maybe you're wondering how we're getting this. So do this. I'm just going to rewrite this the way we usually do it. Derivative of the first times the second. But now for quotient rule, this becomes subtraction, and then derivative of the second times the first, all over g at x squared. So now I'm just going to substitute the information that we have. We have f prime at x is just this. So I get 12x squared times g at x, which is this, minus g prime at x, which is 4x, times f at x, which is 4x to the power of 3 minus 7, all over g at x squared, which is just this squared. And then all we have to do is do some expanding, collecting like terms. So we'll do that right now. So we're going to expand this out using distributive property. We get 24 x to the power 4 plus 36x squared. Distributive property here. We get negative 16x to the power 4 plus 28x, because this is negative 4 into both of these. All over, and I can just leave the bottom here. I don't have to expand the bottom out. Like that. Collect our like terms. I'm left with 8x to the power 4 plus 36x squared plus 28x all over 2x squared plus 3 to the power of 2. So this is the derivative of this. All right, let's try it one more time. We have this, and we're going to be using that quotient rule to find the derivative of this. So I know I have g at x here. I'm just going to change this to q again because I'm used to doing our f at x and g at x up here. So let's do that again. F at x is going to be 4x plus 1. The derivative of that is just 4. For g at x, we have, again, I have a square root here. I'm going to turn that to an exponent. 1 minus x to the power of half. Then the derivative of that, bring that exponent to the front, subtract it by 1, and then take the derivative of the inside of the brackets, which is just that. So now that I know that, I'm going to just rewrite my quotient rule equation, where we have q prime at x is equal to f prime at x times g at x, derivative of the first times the second, subtract derivative of the second times the first, all over g at x squared. So we fill in what we know. F prime at x is equal to 4. G at x we said is 1 minus x to the power of half minus g prime at x is half 1 minus x to the power of negative 1 over 2 times negative 1, and then times f at x, which is 4x plus 1. And then g at x here is just 1 minus x to the power of half to the power of 2. That's what g at x is, and that's to the power of 2. So my next step now is I can simplify this, and I can simplify part of the top as well. So let's just do that quick. I'm going to have 4, 1 minus x to the power of half, and then negative half times negative 1, I can just change this to plus half 1 minus x to the power of negative half 4x plus 1. Sorry, I think I mumbled that. So we did our derivative here. So then we just did negative half times negative 1 gives me positive half. And then just the rest follows 1 minus x to the power of negative 1 over 2, and then 4x plus 1. And I can also simplify the bottom here, because exponent laws, I can multiply these. I get 1 minus x to the power of 1, or just 1 minus x. So now, like before, we're actually going to common factor something. We're going to, well, but this time we're only doing it from the numerator. So just from the numerator, we're going to common factor something. What things in brackets look the same there? I don't see any other 4x plus 1, but I do see this 1 minus x here. So I compare the two. Oh, we have two exponents. One is positive and one is negative. So I always have to do common factor by the lower of the two, so I'm going to common factor this. I'm also going to common factor the half out of this as well, because we see when we do the common factor, we're going to get some whole numbers. So I'm going to common factor half 1 minus x to the power of negative 1 over 2. So I'm going to show this common factor just from the numerator. So everything is still going to be over this 1 minus x here. Oops, I had this left over. So I'm going to get my numerators, which is this 1 minus x to the power of half plus half over 1 minus x to the power of negative half times 4x plus 1 all over this common factor of half 1 minus x negative 1 over 2. So when I do this, I bring my common factor to the front. And now I do my division here. So I'm dividing these two terms. So 4 divided by half will give me 8. You can check that on your calculator. 4 divided by 0.5 should give you 8. And since these are the same base, I'm going to subtract these exponents. 1 over 2 minus negative 1 over 2. Well, that double negative turns into a positive. So I get 2 over 2, which is just 1 minus x to the power of 1. These cancel out here. So I'm just left with plus 4x plus 1. This is still over 1 minus x. So remember my exponent here is 1. So I can actually just do some subtraction here as well. Negative 1 subtract 1. 1 minus x, negative 3 over 2. And I can actually start collecting like terms here. I'm going to get 8 minus 8x plus 4x plus 1. I can do this with a fraction. I mean, this half is technically a fraction, so I have a denominator here. And I can just put this to the bottom as well. So I'm going to get 1 over, the denominator is 2. I'm moving this to the denominator, so I can change the sign. And then I just have the top here, which I can collect my like terms. I'm left with negative 8x plus 4x. Which should give me, well, I can do the 8 plus 1 also is just 9. And this is going to be minus 4x here. Then I'm pretty much done. If I want, I can just kind of leave it like this. I can put the square root back in if I want to. Just multiply this by 1. This is good. Oops, sorry, this is just my exponent of 3 over 2. And I got 3 over 2 again because when I subtracted these, negative 1 over 2 minus 1 would give me negative 3 over 2, and then I move this to the bottom of the fraction to make it positive. So yeah, there's a lot going on in here. Hopefully you're able to follow along. If you're not, just let me know, and we can go over it again. So we just have one more example to do. Alright, last one says, suppose the function this represents the value v in dollars of a new car years after it's purchased. So what is the initial value of the car? Well, the initial value has to be when no time has taken place since you bought the car. So this happens when t is equal to 0. I could just put 0 into both of these. Well, this will become 0. That'll be 0. My initial price of the car when no time has gone by is just 50,000. Again, 0, 0, so 50,000 over 1 is just 50,000 there. Now it says, what is the rate of change of the value of the car at 2 years, 5 years, and 7 years? So we just have to get our equation here and find the derivative because we're finding rate of change. V at t is equal to 50,000 plus 6t over 1 plus 0.4t. So again, f at x we can say is the numerator, and then the derivative of that is just 6. G at x is 1 plus 0.4t, and then g prime at x is equal to 0.4. So again, I'm going to do my quotient rule equation. So then we just fill in what we know. 6, 1 plus 0.4t minus 0.4 times this. All over 1 plus 0.4t squared. So we can just do some distributive property here. 6 plus 2.4t minus 20,000 plus 2.4t all over this squared. I can do the negative into the brackets now. Sorry, just set that in the denominator again. So just simplifying the numerator again, well, this and this, and the t's kind of cancel out, so I'm just left with negative 11994 over this denominator. So could I expand this further? I could, but we already have the derivative here. I really just have to find it, what is the value, or the rate of change at these times. So we're going to have v at 2, then at 5, and then at 7. I'm actually going to leave the rest of this up to you, because once we have this, we just put t into t here, solve, and we'll get a value. So then you can solve for that one once we have this now. So, I mean, we could have stopped way earlier for this question if we wanted to. We could have stopped here if we wanted to. But then we're getting very close again to first principles, and the whole point of us learning these derivative rules is that I don't have to use first principles. So I can simplify things, and then once I have a simplified equation, I can just use this equation for these three, instead of having to go all the way back to do maybe this step or from here on out. So that's it for our 2.5 note, sorry. There's a part here that says, how can these values be used to support the argument that sometimes purchasing a used car is better than a new one? Well, we're going to see that when you buy a new car, the value, or the rate of change of the value, decreases. So the car is going to be worth way less than it is than when you bought it. So you can write that down if you want to. Maybe we'll talk about that in class, or I'll go over it quickly in class. But that's it for the note. Thank you very much for your time.